In this short video, I'm going to explain the setup of an electrogravimetry experiment in which copper 2 ion is plated from solution onto the surface of a copper screen. In the picture you can see the apparatus we'll be using. I have a hot plate and mixing plate combined. We'll be heating and mixing. A 150 ml beaker, and there's a piece of copper mesh. It folded inside the beaker. Now the copper mesh is cut to the height of the beaker, and the length of it is enough that it wraps at least, say, 1.5 times around the beaker. Now that copper mesh has to fit tightly against the inner wall of the beaker, which isn't a problem because when you coil it, it wants to uncoil anyway. The point is you don't want any of the copper mesh contacting the anode, because that'll short the circuit. So even before you start, check that there are no strands of copper wire that are loose that could be protruding to the center and short the circuit. Either cut those off or fold them in, and then you'll want to weigh that copper mesh initially when it's clean and dry on the analytical balance to get an exact mass before you put it in the solution. You'll also need a 1-inch mag stir bar and a piece of carbon graphite to serve as an anode. In the picture it's currently clamped by a 3-finger clamp above the solution. You'll need some cables, a couple of alligator clips, 2 multimeters, and a DC power supply. Now I'll explain more about the connections in a minute, but let's look at the preparation of the solution first. To prepare the solution, you can take a 150 ml beaker and tare it on a 4-place analytical balance and add approximately 0.4 grams of copper 2 sulfate pentahydrate, but record the exact mass to 4 decimal places. Then you can take that beaker back to the lab and add 98 mils of distilled water. I simply used a graduated cylinder. Then add 2 mils of 1:1 nitric acid, and that'll bring the total volume to 100 mils, which makes easier for calculations later on. The nitric acid I added with a 2 ml volumetric pipette. Finally, on a top loader balance, you can add approximately 0.5 grams of sulfamic acid. The exact mass is not that critical in this case. And it goes without saying that at some point here you'll want to add your 1-inch mag stir bar and stir the solution until it's homogeneous and all the solids are dissolved. You can see the pale blue color of the solution owing to the presence of copper 2 ion. Now as the plating proceeds, that blue color will gradually fade until it becomes colorless. That'll be one of the indications that the plating has gone to completion. More about that later. So let's go back to our setup. You'll notice that the copper cathode mesh is connected with an alligator clip to a black cable which goes through an ammeter and then to the negative terminal of the power supply. And that means that electrons will flow out of the negative terminal of the power supply and to the surface of the copper mesh cathode. And those electrons will then be transferred into solution, and the copper 2 ion in solution will accept the electrons. The copper 2 ions will be reduced and plated as copper metal. Now recall that reduction always occurs at the cathode, and that's why our copper mesh is referred to as the cathode. Sitting above the solution you see the carbon graphite anode connected by a yellow wire that goes directly to the positive terminal of the power supply. So electrons will be taken into the positive terminal of the power supply, and they'll be taken from the surface of the carbon graphite anode. So that means something has to be oxidized to give up those electrons. Well, what is it? Well, likely it's water. So water at the surface of the anode will be oxidized to oxygen. We'll be running this at 1.8 volts, and that's enough voltage to oxidize water to oxygen. Now the presence of gas bubbles of oxygen at the anode is not a problem, but we would not want to have any gas bubble formation at the cathode, because that creates a plated material that doesn't adhere well. It's spongy and it tends to fall off. We need all that copper to adhere to the copper mesh so we can weigh it. Now, copper is certainly the first species to be reduced. Its reduction potential is favorable. It's plus 0.34 volts, but not far behind that is hydrogen ion. Its reduction potential is 0 volts. Now, a voltage of 1.8 volts is sufficient to reduce hydrogen ion to hydrogen gas at the cathode as well, possibly forming some hydrogen bubbles, which would interfere again, as I described, with the adherence of the copper metal to the cathode. So that is the purpose of the nitric acid. Nitrate ion in acidic solution is a pretty strong oxidizer, and it would like to be reduced. So as the copper is being reduced, the second most likely species to be reduced would be the nitrate ion, but it does not reduce to a gas. It reduces to ammonium ion, which stays in solution. So basically this occurs in preference to the reduction of hydrogen ion. The nitrate ion is termed a depolarizer in the sense that it reduces charge separation. It prevents this formation of gas bubbles at the surface of the cathode to ensure a better adhering copper plate. You'll notice that we also have a voltmeter connected in parallel so that we can carefully set and control the voltage. Now let's take a look next at the Kakusui power supply and talk about the settings there. You'll notice the power supply has two sets of current and voltage dials. The set on the left are for controlling 0 to 6 volts DC. We'll be using these two dials. The dials on the right side are for controlling 0 to plus or minus 20 volts. We will not use the right hand side dials. Notice the meter select switch in the center of the supply is pushed to far to the left, which means we'll be using the 0 to 6 volts DC supply. Before the power switch is turned on, you'll have the instructor check your electrical connections to make sure they're correct, and you will also turn the current dial fully clockwise, allowing maximum possible current. That doesn't mean you'll get maximum current. It means it's not restricted and you'll get as much current as you need, and that's determined by the voltage setting. So set the voltage to 0, that is, turn it fully counterclockwise. When the power switch is turned on, leave the current dial at maximum and gradually increase the voltage dial clockwise until your multimeter says it's 1.80 volts. And the power supply will control that at a constant 1.8 volts. And that's why it's called constant voltage control. So here we have the solution of copper 2 sulfate and nitric acid and sulfamic acid and the copper screen inside it. It looks like it's all ready to go, but I want to point something out to you. Nitric acid dissolves copper, and that's exactly the opposite of what we're trying to do. We're trying to get copper to plate out of solution. We're not trying to dissolve the copper screen. Now, we've diluted our nitric acid quite a bit. We started with 8 molar, that's 1 to 1, and we diluted it by a factor of 50 times, from 2 mils up to 100, and so it's pretty dilute. The point is, you don't have to panic. It's not going to dissolve quickly. It'll take some time to do so. Nonetheless, what I'm saying is, before you put the copper screen into the nitric acid solution, have everything else set up ready to go. Have your wires connected, your multimeter set, have your power supply set, have the instructor check it. And then once you put the copper screen in, don't race, just relax, but don't waste any time in turning on the power supply to start the electroplating. Now let's take a look at the graph of current versus elapsed time. The ammeter is set to the 0 to 200 milliamp scale. When you first turn on the power supply and increase the voltage to 1.8 volts, the current will be off scale high, but don't worry about it. It'll drop within seconds to be within the range where we can read it. Now, if you look at about the 4 minute mark here, you'll see that the current is gradually increasing. And the reason it's increasing is because I've turned the hot plate on to the surface temperature of 50 degrees C. So between about 5 minutes and 60 minutes, the solution gradually heated from room temperature to slightly over 30 degrees Celsius, and that heating increases the rate of deposition. And that's favorable. It reduces the overpotential and increases our rate of plating. Now, we could go hotter, and that would make it faster, but then we'd be potentially exposing ourselves to nitric acid fumes, and so we don't want to do that. Once the time reached about 60 minutes, the current suddenly began to drop quickly, and that's an indication that the bulk of the copper has been plated from solution, and so the rate of current flow drops accordingly. Alright, so there's a few more images to show and we'll wrap this up. Here is a photo of the carbon graphite anode centered very carefully inside the copper mesh during electrolysis. Again, you want to make sure these do not touch or you'll short the circuit. You'll be recording the current in milliamps, the voltage, and the elapsed time at least every 5 minutes. And as you're taking your data, also plot the current in milliamps versus elapsed time so you can monitor the progress and you'll know about where the reaction has reached completion. Once you have your first 1 or 2 readings under your belt and things have calmed down, it would be a good time to run your first copper amine test. So here there's still copper in solution, and I want you to see what that looks like. So take a Pasteur pipette and take about, say, 2 drops from the plating solution. You don't have to stop it, keep it running, but just carefully take 2 drops in a clean test tube and put in 2 or 3 drops of concentrated ammonia. Do that in the fume hood. And notice the bright blue color that's formed from the tetraamine copper 2 complex. And it's more distinctive than the blue color of solution, so it'll help you visually identify when the reaction has reached completion. Here's an example of a solution. The plating was stopped, and you can see if you look closely there's still a pale blue tinge in the solution, but look how bright the blue color is in the copper amine test, indicating that copper is still present in solution. Once all of the copper has been removed from solution, the solution will be colorless, and the copper amine test solution in the test tube will be colorless. Each time you take a couple of drops for the amine test, don't bother putting it back in the plating solution. We don't want to add ammonia to the nitric acid. The losses will be negligible. It shouldn't have any significant effect on your mass calculations. Here's the picture of a screen that has been removed at the end of the plating. Now, once you figure you're done and you want to remove the copper, don't waste any time. Once you shut the power supply off, don't rush, but again, don't waste time in removing the copper screen. We don't want that copper to redissolve into the solution. Now, handle the screen carefully. If you crush it, you may knock some of the copper off it. Rinse it generously under the tap, and then you can dip it in a solvent like acetone or alcohol such that when you take it, it'll dry quickly and you can get your final mass. Check with the instructor what to do with your plating solutions and put all your equipment away. Make sure the meters are turned off. And then check the lab procedure to see what calculations are required and how to do them. So I trust at this point you are able to carry out this experiment. All the best.